So those are the announcements, the worksheets, the homework number 3 are due on the 30th, and you'll have the test on the 30th, which is begins next week on Thursday. Otherwise, I think everything's more or less okay. Let's continue. Oh, click on the screen. So we were talking about the deaths of stars. We're talking about what happened when a star ran out of hydrogen in its core and expanded to become a red giant. And now we'll finish off with how the actual final stages of the life of the star end. The actual final death of a star. So this is the Helix Nebula, which is a planetary nebula. The central white dot is the hot white dwarf at the center, which is the core of the star that this nebula used to be. So this is the lifespan of a star. Starts as a cloud of gas and dust, becomes a protostar, becomes the star, then expands into a red giant, finally blows off its outer layers and becomes a white dwarf, which will just sit there and cool. So when double shell fusion ends, there's a pulse that ejects hydrogen and helium out into space as a planetary nebula, and the remaining left behind core becomes a white dwarf. This is just a hot ball of usually mostly carbon held up by electron degeneracy. So planetary nebulas can look various ways. This is one. This is a different one. Their shapes can be quite varied because often stars are in binary systems. They can be affected by that. They can sort of explode and blow off their outer layers in different ways. So here, the butterfly nebula, the hot white dwarf, is hidden in the ring in the center. So the way that a planetary nebula forms, as the star becomes very large, the escape velocity becomes low because gravity is proportional to mass and distance. So as you increase the distance, you need less speed to escape. And so the outer layers aren't held very strongly. And eventually the outer layers get expelled out into space to become a planetary nebula. So there's no more outward fusion pressure being generated in the star, which will in the core, which will continue to contract. The outer layers of the star expand to form a planetary nebula. So there's now 2 parts: a small, extremely dense carbon core, and an envelope about the size of our solar system floating out into space. The envelope is called a planetary nebula, even though it doesn't have anything to do with planets, because early astronomers thought this fuzzy envelope resembled a planetary system. And then the extremely dense carbon core is called a white dwarf. And that is, a corpse of a star. And planetary nebulas can be quite different because many stars are in binary systems and the nebulae will change over time. They're not very long-lived in astronomical time. This stage only lasts about 50,000 years because the nebula is sort of floating out into space and eventually disperses. And this is one way enriched material with heavier elements in it is expelled back into space. So this was, this is the final life track of a sun-like star. Becomes a red giant, it expands into a subgiant, a red giant becomes a helium core fusion star, a double shell fusion red giant, blows off the outer layers as a planetary nebula, and the core remains as a white dwarf. I think it's just yeah. So fusion doesn't progress any further in a low mass star because the core temperature never gets hot enough for the fusion of heavier elements. Some helium will fuse with the carbon in the core to form oxygen, but not a lot. So the white dwarf is supported against gravity by degeneracy pressure. And it becomes basically a ball of carbon, mostly carbon, that's on the same scale as the Earth, with a mass on the same, around the same scale as the sun. So in the later stages of a sun-like star, the helium will be fused into carbon, the star will build up layers in its interior, and the outer layers of the star will be expelled out into space as a planetary nebula. So after the planetary nebula, these outer layers were ejected out into space. What happens to the core? So we're going to talk about white dwarfs if cores are less than 1.4 solar masses. So this is stars up to about 8 or 10 solar masses initially. But this is the core of the star. If the original star was about 10 solar, up to 10 solar, less than the 10 solar masses, its core will be less than about 1.4 solar masses. And this core is a white dwarf. And the white dwarf is, the core of a star. It's just a ball of hot, mostly carbon, held up by electron degeneracy.
Welcome to an overview of the chapter titled The Bizarre Stellar Graveyard. In this video, we'll introduce a few of the key learning objectives for the chapter. In particular, we'll recognize that degeneracy pressure balances gravity in white dwarfs and neutron stars, describe how a white dwarf in a binary star system can explode as a supernova, explain how neutron stars are detected, and describe the evidence indicating that black holes really exist. At the center of this X-ray image is one kind of object that can remain after a star dies. In this case, it is a compact ball of neutrons, known as a neutron star, that is more massive than the Sun, but no larger in diameter than a modestly sized city. Our task in this chapter is to understand the properties of, and evidence for, neutron stars and the other strange objects that represent end states of stars. Recall that a normal star has two kinds of balance: gravitational equilibrium, in which pressure balances gravity, and energy balance, in which fusion releases energy in the core at the same rate that the star radiates energy to space from its surface. However, as discussed in the prior chapter, near the end of a star's life, the energy balance is broken each time the star runs out of a fuel for fusion. Gravity then overwhelms pressure, causing the star's core to contract. Balance can be restored if a new fuel for fusion ignites in the core, and this process can repeat several times depending on the star's mass. Ultimately, however, the star will exhaust all fuel for fusion, and gravity will once again overwhelm pressure. With no fuel left for fusion, the only hope the core has of halting the crush of gravity lies with degeneracy pressure, the strange type of pressure we encountered when we discussed brown dwarfs. Recall that degeneracy pressure arises when the laws of quantum mechanics prevent subatomic particles from becoming more tightly packed, for which we used the analogy of students in a room in which there are not enough chairs to give students options on where to sit. For relatively low-mass stars, the dead core becomes a white dwarf, which is supported against gravity by degeneracy pressure created by electrons being packed as closely as the laws of quantum mechanics allow, or electron degeneracy pressure. Because degeneracy pressure does not depend on temperature, this stalemate between pressure and gravity can last indefinitely, so an isolated white dwarf will cool with time, but never again change in any more fundamental way. The size of a white dwarf depends on its mass. A white dwarf with the mass of our Sun is only about the size of Earth, giving it such a high density that a teaspoon of white dwarf material would weigh several tons if you could bring it to Earth. More massive white dwarfs are even smaller and denser because their stronger gravity packs the electrons even closer together. However, in order to occupy a smaller amount of space, the laws of quantum mechanics also demand that the electrons move faster. This means that there is a limit to the maximum mass of a white dwarf because electron speeds cannot exceed the speed of light. Both models and observations show that this white dwarf limit is about 1.4 times the mass of our Sun. This fact can lead to dramatic events for white dwarfs in close binary systems, in which gas from a companion star forms an accretion disk as it falls inward toward the white dwarf. Friction within the disk converts the orbital kinetic energy of the gas particles into thermal energy, making the disk hot enough to glow brightly in ultraviolet light. Hydrogen gas accumulating on the white dwarf's surface eventually becomes hot enough for fusion, which ignites with a sudden outburst called a nova, producing a spike in brightness that we can detect on Earth and which lasts for a few months. An even more dramatic event will occur if the white dwarf ever accumulates enough mass to reach the 1.4 solar mass limit. At that point, it can no longer remain a white dwarf. Instead, an enormous outburst of fusion completely destroys the white dwarf in the explosion we call a white dwarf supernova. Astronomers can identify white dwarf supernovae because their light curves differ from massive star supernovae, as shown on this graph.
So, what is a white dwarf? So here we have a binary star, Sirius A and Sirius B. This is in X-rays. Sirius B is a white dwarf. It's very small, but here in X-rays and ultraviolet, it is outshining Sirius A because of material coming off Sirius A and accreting on to Sirius B. So white dwarfs are the remaining cores of dead stars. They're supported against gravity by electron degeneracy pressure. And so the core will contract until it becomes degenerate. This means electrons are pushed as close together as possible. They hit a quantum mechanical limit based on the Pauli exclusion principle that says that two electrons can't be in the same place at the same time doing the same thing, basically. And electron degeneracy pressure supports the core against gravity. And the core will become a stable white dwarf. That is about the size of the Earth. If it's less massive, it's a little bigger than the Earth. If it's more massive, it's a little smaller than the Earth. One of the funny things about things supported by degeneracy. The density is about 1 million times the density of water. And without external influences, it'll just sit there, remain stable forever, and slowly cool. Okay. So this is sort of the last stage, the white and black dwarf. So once the nebula is gone, the remaining core is extremely dense and extremely hot, but quite small. And it's only luminous, it's only glowing because of its high temperature. It is very hot, so it glows. But it's not very luminous because it's tiny, because it's only like the size of the Earth. And it will slowly cool until it stops being visible and becomes what is called a black dwarf. However, we do not think there are any black dwarfs out there because the universe isn't old enough. Because the time scale for it to slowly cool is so long that we don't think enough time has passed in the existence of the universe for any white dwarf to cool down enough to become a black dwarf. So, some of the ways we can find white dwarfs. We can see them visually. So we have that previous picture in X-ray and ultraviolet. This is invisible. This is Sirius A. This is Sirius B. It's the tiny dot down here. They're also detected in binary systems. If you have two objects, if you have a star orbiting basically an invisible object, and that object has a mass that's, between about 8% and 1.4 solar masses, it's probably a white dwarf. And we also detect mass transfer from the ordinary star to the white dwarf. That's another thing we can see. So here in Sirius B, if you look at X-rays or ultraviolet, with Sirius A is much dimmer than Sirius B in X-rays and ultraviolet because the accreting material onto Sirius B ends up much is putting out a lot more energy in that range. So you have material going from its partner star and accreting onto the white dwarf. And as it builds up, every once in a while, that white dwarf will undergo a nova because material will build up on the surface, and eventually enough material will build up and get hot enough to undergo fusion, and you basically get a big hydrogen fusion explosion. And there's in fact a star that we're expecting to go nova sometime soon, and as in fact we were expecting it to go nova sometime last year. It still hasn't gone nova yet because we don't have a perfect understanding of these, but it's sort of, this is a sort of repeating pattern. So as material builds up until it goes nova, and then more material accretes and it builds up and then it goes nova. So there's a star that people have been expecting to go nova sometime soon, but hasn't yet. So one of the things that happens here is you get what's called a nova. So the small star Sirius B here is a white dwarf companion of the much larger and brighter Sirius A. And the Hubble Space Telescope has detected white dwarf stars in globular clusters. In these, old clusters of stars. And these white dwarfs will cool off and grow dimmer with time. So they'll steadily cool, but the time scale for that is very long. So what happens to a white dwarf star as it cools? It doesn't have an energy source, so it's just going to cool down. And so as it cools down, it will change from white to red to black to infrared. It'll move to longer and longer wavelengths as the temperature decreases. But it's very small, quite massive. Because it is very small but also quite massive, there's a lot of stored energy thermal energy that it needs to bleed off. And that takes a long time. So the small size means the star cools slowly. After many billions of years, it will become dark and be considered a black dwarf. But the time scale for that is literally longer than the current age of the universe. So no such stars have had time to form in the history of the universe. So let's talk about the size of a white dwarf. White dwarfs with about the same mass as the sun are about the same size as Earth, while because of the way that gravity and degeneracy pressure interact, more massive white dwarfs have stronger gravity, so they end up smaller. A similar thing happens with other things supported by degeneracy. As they get more massive, they get smaller. But it turns out there's a limit. So there's a limit. If you work this out without relativity, you can work out the radius of a white dwarf as a function of its mass. That's that blue line. But we live in a world with relativity. So when we start taking into account relativity, it turns out as these white dwarfs get smaller and more compact, the electrons have to move faster and faster. And eventually they would end up having to move faster than the speed of light. So that's the point where degeneracy pressure stops working. So that's this cutoff. This line here, it's called the Chandrakar limit, or the Chandrakar mass, because it was discovered by Chandrakar. And it's about 1.4 solar masses. And once you hit that point, you've hit the ultra-relativistic limit, and your white dwarf will start collapsing because degeneracy pressure will be overcome. And what happens if you have an existing white dwarf, you add enough mass to hit this limit, Well, the white dwarf starts collapsing. It gets hotter and hotter. It's a big ball of carbon that's getting hotter and hotter. Eventually, it gets hot enough for all the carbon to fuse, and it goes off like a bomb. So quantum mechanics says that while electrons have to move faster as they're squeezed into a very small space, as a white dwarf's mass approaches 1.4 times the mass of the sun, its electrons need to move at nearly the speed of light. Because nothing can move faster than light, a white dwarf can't be more massive than about 1.4 times the mass of the sun. And this is the white dwarf limit. It's also known as the Chandrasekhar limit. And so this was discovered by Chandrasekhar. He did the calculations. We also see this. We don't see white dwarfs bigger than 1.4 solar masses. And if a white dwarf has mass added to it, because it's in a binary partner, it's steadily adding mass, if it hits the point where it's at 1.4 solar masses, it will collapse and go supernova. It will explode. The entire star will undergo fusion simultaneously, and it will violently explode. So how massive can the final core be? So electron degeneracy can support a core up to 1.4 solar masses. And because of the pressure, white dwarfs with larger masses get smaller in size. If you have a more massive core, it will be unstable and continue to collapse. Now, if that more massive core is occurring in a star that's dying, you get something different than if that massive core is, just a white dwarf that you added mass to. Those are two different situations. So a 6 solar mass star needs to lose 4.6 solar masses to become a white dwarf. That's over 75% of its mass. Is this possible? And evidence from star clusters says yes, because we've detected white dwarfs in pretty young clusters. So we've detected white dwarfs in clusters where only stars that are more massive than 6 solar masses have had time to evolve. So stars with 6 solar masses must be able to lose over 75% of their mass. Our general belief is that the line between whether you get a white dwarf or a neutron star is around 8 to 10 solar masses. So stars less than about 10 solar masses will leave behind a white dwarf. Stars greater than about 10 solar masses will go through a supernova and leave behind a neutron star or a black hole. Now, when a white dwarf is in a close binary system, it has another star it can grab material from. And this can lead to some interesting effects. So in a close binary, one star can steal mass from the other. And the mass falling towards the white dwarf from its close binary companion has some angular momentum. So it will orbit the white dwarf in an accretion disk. This accretion disk will heat up, glow, lose energy steadily that way. So the friction between the orbiting matter, rings of matter, and the disk will transfer angular momentum outward and cause the disk to heat up and glow. And this will allow material to settle onto the white dwarf. And the temperature of the accreted matter eventually becomes hot enough that fusion can occur for hydrogen fusion. And you'll have your disk basically suddenly and explosively undergoing fusion, causing a nova. And you'll have the steady accretion of material onto the white dwarf, which takes time. So the nova star system here will temporarily appear much brighter, and this explosion will drive some of the accreted matter out into space, so not that much extra material is going to be built up on the white dwarf. So a nova is the star that will flare up suddenly and then return slowly to its former luminosity. It's called a nova because often these were very dim, so it will look like a new star, nova. And often, for some stars, novas are periodic. They'll happen over and over again. So one of the things we're looking towards is that there is a nova that should be visible with the naked eye, hopefully coming up soon. So a white dwarf that's part of a semi-detached binary system, it can undergo repeated novas. You could build up matter, nova, build up matter again, nova. And so you could expect these novas to repeat. So material that falls from on the white dwarf from its main sequence companion. When enough material has been accreted, fusion can reignite very suddenly. And material keeps being transferred to the white dwarf, so the process will repeat. Now, there's also a supernova, and they come in two types. There is a massive star supernova, where the iron core of a massive star reaches the white dwarf limit and collapses into a neutron star, causing an explosion. So that's what happens with really big stars. And then there's a white dwarf supernova. This is where carbon fusion suddenly begins as a white dwarf in a closed binary system reaches the white dwarf limit, and this causes a total explosion. White dwarf supernovae are type 1 supernovae, massive star supernovae are type 2 supernovae. And type 1a supernovae, which are a type of white dwarf supernovae, are very useful as a tool for measuring distances because they are all functionally identical. They're all 1.4 solar masses of carbon undergoing sudden simultaneous fusion and blowing up. So we use them to measure distances to distant galaxies. So here are the two types of supernova. They can be differentiated by how their luminosity changes with time. They also have different spectral signatures. And so not that hard to tell them about. So this is a massive star supernova. Doesn't get quite as bright. It cools down in sort of a more irregular manner. But a white dwarf supernova gets very bright and then steadily dims in a more straightforward way. Now, supernovae are much, much more luminous than novae, about 10 million times. So supernovae have been reported to be bright enough that you could actually read by them at night and see them during the day, kind of bright. So a nova is hydrogen to helium fusion in a layer of accreted matter. The white dwarf is left intact. A supernova, a white dwarf supernova, is the complete explosion of a white dwarf. Absolutely nothing is left behind. Now, the last observed supernova in our galaxy was in 16 something. It was by Tycho Brahe, actually, in the 1600s. There hasn't been a supernova in our galaxy since. But we have observed some in some close by galaxies. So we can differentiate them by their light curve. The way they brighten up and dim differs for a massive star supernova and a white dwarf supernova, and the spectra differ. When white dwarfs explode, they don't have hydrogen absorption lines because they're just a ball of carbon blowing up. There's no hydrogen there. While in a massive star supernova, there's the whole outer layers of the star in the way. And in a massive star supernova, you don't have fusion of the core because it's iron, and there's no fusion you can pull off. So, some effects from supernovae. They create heavy elements. When supernovae happen, this is how you can get elements heavier than iron. Because so much energy is released, it can cause fusion of iron, even though fusion of elements heavier than iron, even though no energy is gained. They also enrich the interstellar medium with heavy elements to form the next generation of stars. They distribute heavy elements. So there are various nebulae that are remnants of supernova from large star explosions. So the Crab Nebula, for example, is a remnant of the 1047 supernova explosion. And a nearby supernova could be devastating to life on Earth. If it was within 50 light years, it could wipe out all life. If it was in 100 light years, it could still cause extinctions due to radiation levels. Fortunately, we don't actually have to worry about this. It sounds horrible and disastrous, but there aren't any stars that can go supernova within that distance of Earth. So we don't actually have to worry about that particular end of the world scenario. So here are some historical supernovae. Supernova 1006 was recorded by multiple sources, and the remnant is visible at the described location in the constellation Lupus. So this is the remnant of supernova 1006. They're generally named after the year they were found. Supernova 1054, the year they were occurred, sorry. This is the Crab Nebula in Taurus. This is the remnant of that. This was a massive star exploding. There is a neutron star in the center of it. Then there was Tycho's supernova in 1572 and Kepler's supernova in 1604. And amusingly, no supernova have been observed in our galaxy since the invention of the telescope. So since we invented telescopes where we can look at things, no supernova have happened in our galaxy. The nearest supernova since the invention of the telescope happened in 1987 when I was 3. Actually, I'm not even sure I was 3 at that point. I think I was 2. So this occurred in the Large Magellanic Cloud, which is one of the small galaxies orbiting the Milky Way. And this is the first, it occurred February 1987 in the Large Magellanic Cloud. And this is the first time the progenitor star had been seen. This is the first time we saw a supernova where we had observed the star beforehand. And it was surprising because the progenitor star was a blue supergiant. It wasn't expected to form a supernova. And here is an image of the expanding material from the explosion as seen today. So as a low mass star ages, the outer layers get expelled as a planetary nebula, and the core will contract to become a white dwarf. A white dwarf is 1 million times denser than water and about the size of the Earth. And a white dwarf will slowly cool over time to eventually become a black dwarf. So now we talk about low mass stars and what happens with them. Low mass stars kind of go out with a whimper. They just blow off their outer layers and leave their core behind. High mass stars go out with a bang. We mentioned the high mass star supernovae. In high mass stars, because they can fuse elements to elements that are heavier than, say, just carbon, you can get a much more violent end to your star. So all elements greater than hydrogen and helium basically have to be produced in some process with stars. And we'll see, you can see this sort of pattern. There's a few elements here, lithium, beryllium, boron. They're all quite rare. And then in general, we'll see that starting at carbon, we see this alternating pattern. The even numbered elements are more common than the odd numbered elements. And that's because fusion generally happens for heavier elements by merging with helium nuclei. Once carbon is formed, it turns out you can't get 2 heliums to fuse nicely. So you go from helium to carbon. So these elements, lithium, beryllium, and boron, have to be generated by other processes that involve supernovas. But we'll see this sort of alternating pattern, where even numbered elements are much more common than odd. And that's because what happens is you steadily add helium nuclei, and so you jump up by 2.
The science of modern astronomy tells us that most of the elements of which we and our planet are built were produced by stars. This graph shows crucial evidence that supports this idea. In this video, we'll discuss this graph and how it lends support to the idea that we are made from star stuff. The graph shows how the abundances of various elements in our galaxy compared to that of hydrogen. Recall that atomic number, shown on the horizontal axis, represents the number of protons in an atomic nucleus. Each atomic number corresponds to a different element of the periodic table. For example, atomic number 1 is hydrogen, atomic number 2 is helium, and atomic number 26 is iron. The vertical axis shows how the abundances of various elements in our galaxy compared to that of hydrogen. The abundance of hydrogen is therefore set as 1, since we are measuring other abundances relative to it. Notice that the first tick mark as we go down is labeled 10 to the minus 2, which is 1/100th, so if any element had this abundance value, it would mean there were 1% as many atoms of this element as atoms of hydrogen in the galaxy. The next tick mark is 10 to the minus 4, or 1/10,000th. Nitrogen is close to this value, telling us that there is 1 nitrogen atom for about every 10,000 hydrogen atoms in the galaxy. Elements with lower abundances are even rarer in the galaxy. Now consider this question. Helium is clearly the second most abundant element, but what is the third most abundant? Is it lithium, carbon, oxygen, neon, or iron? The answer is C, oxygen, because it has the third highest dot on the graph. Notice that its abundance is about 10 to the minus 3, or 1/1000th, telling us that the galaxy contains about 1,000 times as many hydrogen atoms as oxygen atoms. The fact that hydrogen and helium are the two most abundant elements is consistent with the idea that these two elements were produced in the Big Bang. Beyond that, the patterns on this graph allow us to test our models of how elements are made by stars. For example, the 3 elements with atomic numbers 3, 4, and 5 are extremely rare. From there, we see a pattern in which elements with even atomic numbers, such as carbon with atomic number 6, oxygen with atomic number 8, and neon with atomic number 10, are more abundant than the odd-numbered elements that come between them. Also notice the fairly steep drop-off in abundance for elements with more protons than iron and nickel. To begin making sense of these patterns, recall the way elements are forged in low-mass stars. Near the end of its life, the core of a low-mass star becomes hot enough to fuse helium. This reaction fuses 3 helium nuclei into 1 carbon nucleus, releasing energy in the process. The helium nuclei each have 2 protons and 2 neutrons, which means they have atomic number 2 and atomic mass 4. The carbon nucleus has 6 protons and 6 neutrons, for atomic number 6 and atomic mass 12. Because this fusion reaction converts atomic number 2 into atomic number 6, it essentially bypasses atomic numbers 3, 4, and 5, which is why those 3 elements are so rare. Low-mass stars die after their helium fusion stage, but the stronger gravity of high-mass stars allows their cores to reach temperatures high enough to fuse heavier elements. Models tell us that one set of reactions proceeds as helium nuclei fuse into successively heavier elements. For example, helium can fuse with carbon to make oxygen, with oxygen to make neon, with neon to make magnesium, and so on. Many other reactions also occur as the core temperature rises higher, but models indicate that some of the most common should include the fusion of carbon and oxygen to make silicon, 2 oxygens to make sulfur, and 2 silicons to make iron. Notice that all these relatively common reactions produce nuclei with even atomic numbers, which is why these elements are more common than the odd-numbered elements between them. The many fusion reactions begin successively in high-mass stars. Each time the core becomes depleted in the elements it is fusing, it shrinks and heats until it becomes hot enough for the next fusion reactions. Meanwhile, the prior type of fusion can continue in a shell surrounding the core. Near the end of its life, the high-mass core resembles an onion, with layer upon layer of shells fusing different elements. In the final stages of the star's life, iron piles up in the star's core. This marks the end for the star, because iron fusion requires energy input rather than releasing energy, which means it cannot help support the core against the crush of gravity. As discussed in your text, the iron core collapses catastrophically, becoming a ball of neutrons and generating the enormous release of energy that we observe as a supernova. The supernova ejects the overlying layers of the star into space, creating a supernova remnant like this one, the Crab Nebula. Supernova remnants therefore contain the elements forged inside stars, and measurements of their contents support models of element formation and the supernova process. Moreover, the fact that the major fusion reactions end with iron explains the steep drop-off in the abundances that occur beyond that. Elements heavier than iron form only through rarer processes, including reactions that occur during and subsequent to supernova explosions, and, perhaps, in rare events such as the mergers of neutron stars. To summarize, the observed abundances of the elements allow astronomers to test and validate models of how elements are produced by stars.
So yeah, to our current understanding, it's not the elements heavier than iron are generated through supernova explosions, reactions during supernova explosions, but also there are various processes involving the mergers of neutron stars and things like that will cause that are required for some of them. And that, you know, it's complicated, but I mean the main idea is they occur in rare violent events. Generally, is how they're produced, so they're much rarer. In a high mass star, one of the things that can happen is something called the CNO cycle. This is part of why there's so much carbon, oxygen, and nitrogen out in the universe. Is that high mass main sequence stars can fuse hydrogen to helium at a higher rate using carbon, nitrogen, and oxygen as catalysts. So basically, by adding hydrogens repeatedly, you start with carbon, you add a hydrogen to turn it into nitrogen. It then decays from nitrogen 13 to carbon 13. You add another hydrogen, turn it into nitrogen 14. Then you add another hydrogen to turn it into oxygen 15, which will decay into nitrogen 15, which will then, you add another hydrogen and you'll spit off a helium and a carbon 12. So you make oxygen 16, but you can also it be unstable and spit off a helium and a carbon 12. And so that whole net reaction occurs, but it uses carbon as a catalyst. Carbon, nitrogen, and oxygen as a catalyst. Now, the life stages of high mass stars are very similar to those of low mass stars. The start is more or less the same. You have hydrogen core fusion in the main sequence. Then you get hydrogen shell fusion as it forms a supergiant. Then helium core fusion, it's still a supergiant. It's a bigger star, so it gets even bigger when it expands. But instead of stopping at helium core fusion, it continues onward. So if stars are many times more massive than the sun, the temperature will continue to rise in the core, and heavier elements like carbon will be able to fuse. So you get multiple layers built up in the star up to a central core of iron. You have sort of an iron ash in the center, silicon and sulfur fusion above that, magnesium, neon, and oxygen fusion above that, carbon and oxygen fusion above that, helium fusion above that, hydrogen and helium fusion above that, and then just hydrogen. So here we have Eta Carinae. This is a 100 solar mass star. It is flinging off shells of material. So it hasn't gone supernova or anything, it's just blowing off its outer layers. And these are enriched in heavier elements. It's undergoing extensive mass loss, but the core continues fusion. Eventually, Eta Carinae here will become unstable and explode as a supernova. There's a point where you build up enough iron in the core that it just can't support itself anymore because iron doesn't fuse and it collapses. But because it's iron and more massive than 1.4 solar masses, what happens is that that core collapses enough with enough force So on this HR diagram, stars from mass to the sun follow very different paths. So they sort of settle on and zigzag back and forth as they fuse more and heavier elements. And eventually move on to larger size and then could violently end. So high mass stars, like all stars, will leave the main sequence when there's no more hydrogen fuel in their cores. And the first few events are very similar to those in lower mass stars. First a hydrogen cell, then a core burning helium to carbon, surrounded by helium and hydrogen burning cells. Now, stars with masses greater than about 2.5 solar masses don't experience a helium flash. The helium burning starts more gradually. And a 4 solar mass star will make no sharp moves on the HR diagram. It'll move smoothly back and forth. So this is again Eta Carinae being unstable. And a star of more than about 8 solar masses, 8 to 10, confuse elements far beyond carbon in its core, leading to a very different fate. As its path along the HR diagram is essentially a straight line. It stays at just about the same luminosity as it cools off. And eventually the star will die in a violent explosion called a supernova. So in various processes, these high mass stars will make the elements necessary for life. The most common way is for helium capture reactions. And this is why we see lots of even numbered elements. Also, when even numbered elements fuse together, you tend to get even numbered elements. But from carbon 12 to oxygen 16, from oxygen 16 to neon 20, from neon 20 to magnesium 24. You're adding a helium each time. And the Big Bang made about 75% hydrogen, about 25% helium. Everything else requires stars. I guess a tiny bit of the lithium would have been formed in the Big Bang, but most lithium is actually not only requires stars, but like supernovae and other violent things. It's actually hard to make lithium. Helium fusion can make carbon and low mass stars. The CNO cycle can change carbon into nitrogen and oxygen. And high core temperatures allow helium to fuse with heavier elements for helium capture. That gives us even numbered elements up to iron, basically. So evidence for helium capture is that the higher abundance of elements with even numbers of protons, as you can see here. And elements heavier than iron are rare because energy is required to make them. You don't get energy out as they form. The core temperatures of stars with greater than 8 solar masses allow for fusion of elements as heavy as iron. So advanced reactions in stars will make elements like silicon, sulfur, calcium, and iron. And so you get a series of nested shells with an inert iron core, silicon fusion, fusion of oxygen, neon, and magnesium, carbon fusion, hydrogen fusion, helium fusion, hydrogen fusion, and then non-fusion hydrogen. Now the limit for fusion is iron, because you can't get energy out of fusing iron. No energy is released by the fusion of iron. So the core, as iron builds up, the core will eventually become unstable, and it will implode, collapse. And this will lead to a supernova. So as the core collapses, the outer layers will collapse. Eventually, what will happen is the core will continue to collapse. There will be a moment where gravity is strong enough to basically push the electrons into the protons and convert them from protons into neutrons and release an enormous quantity of neutrinos, and also pause the collapse of the core. And the collapsing outer layers will bounce off of this and be actually superheated by neutrinos, which is insane. Because neutrinos barely interact with anything. And that leads to the supernova explosion, while the core will collapse to form a neutron star. Or if it's too big, it'll pause there, which will allow the bounce in the supernova, but then the core will continue to collapse to form a black hole. So elements heavier than iron, some are created during the explosion, some form from other violent interactions like neutron star mergers and things like that. So the limit is iron, because basically, as long as you're going up, reactions can happen on this. This is average binding energy. If you're going up, you get energy out. But the peak is at iron. Iron 56 here. So you can break down bigger elements to get smaller elements, like you start with uranium through fission. But to make bigger elements, you need to input energy. So iron's a dead end for fusion because the nuclear reactions involving iron don't release energy. It has the lowest mass per nuclear particle, which corresponds to the highest binding energy. So here fusion releases energy, here fission releases energy. I'd like to move down on this graph. Those two graphs are basically the same graph except upside down because they're graphing slightly different properties that correspond to each other. So the heavy element abundances in stars, open clusters are population 2 stars. They have heavy element abundances or metal abundances similar to the sun. So like our sun is what's known as a population 2 star. Globular clusters, which are much older, are population 1 stars. Their heavy element or metal abundances are much less, 1/10 to 100th of that we see in the sun. And this population 2 stars, those later generations of stars, these heavy elements allow Earth-like planets to form. So elements like iron, silicon, and carbon wouldn't have existed when the earliest stars formed. So as you approach the end of a star's life, each stage takes less time. It takes less time to use up the fuel because of the higher temperatures of the core lead to faster nuclear reaction rates, and the fuel lasts for a shorter time. And the star will quickly reach its limit. Iron will build up in the core. And then the core will implode. So high mass stars die in violent explosions. So iron will build up in the core until degeneracy pressure can actually no longer resist gravity. Then the core will suddenly collapse, causing a supernova explosion. And what will happen is that as it collapses, electrons and protons will get pushed together so hard, they will merge, forming neutrons and neutrinos. Now, the advantage is that neutrons and neutrinos don't have a charge, so they're not repelling each other anymore, so they can collapse even further. So the core degeneracy pressure goes away because electrons will combine with protons, making neutrons and neutrinos. Neutrons will collapse in the center, forming a neutron star. And neutrinos get flung outwards and will actually help superheat the layers above the core, leading to the supernova explosion. Which is kind of insane because neutrinos are famous for not interacting with things. So the amount of neutrinos that are generated is so high that will actually superheat the layers of the star. So energy and neutrons released in supernova explosions enable elements heavier than iron to form, including things like gold and uranium. And the reason we don't really see elements heavier than uranium is because they're unstable. It's not that they don't form, it's that they don't last. There's a small amount of natural plutonium we found on Earth, but it's actually formed by nuclear reactions in uranium deposits. Because plutonium anything heavier than uranium just isn't stable enough to last for long periods of time. So the energy collapse of the core will drive the outer layers into space. The energy released by the collapse of the core. And the Crab Nebula is the remnant of the supernova seen in AD 1054. It was recorded by a number of people. This is the supernova 1987A. Here is the original star before the supernova. And then this is after the supernova. For a few weeks, the supernova shone brightly enough to be visible to the naked eye, and then it gradually faded. So this supernova was visible to the naked eye and in another galaxy. I mean, this is the closest supernova we've observed since 1605. But yeah, it was in another galaxy. So the role of mass. Mass is the primary determiner of what happens at the end of a star's life. It determines its entire life story because it determines its core temperature. So high mass stars have short lives, eventually becoming hot enough to make iron, and they end in supernova explosion. And the key requirement to get a supernova explosion is making iron, because it has to be that fusion dead end. Because when you have a fusion dead end, your core collapses, and your core gets big enough. When it collapses, it can't fuse. Low mass stars, on the other hand, have long lives. They never become hot enough to fuse carbon nuclei, and they end as white dwarfs. So in general, less than about 0.08, that's a brown dwarf. From 0.08 to 0.25, the initial mass, you get what's called a helium white dwarf. It's a white dwarf, but it's made primarily of helium. These stars never get hot enough to fuse past helium. From about 0.25 to 8, you get a carbon-oxygen white dwarf. From 8 to 12-ish, maybe 8 to 10-ish, you get a neon oxygen white dwarf. And bigger than about 10 to 12-ish, you get a supernova. That line where between white dwarf and supernova isn't that well understood, because they depend on the not very well known amount of mass that was lost while a star lives on the main sequence and other parts of its life. Like, we can figure it out from the late end, but we don't really know exactly how much stars lose mass-wise during the long portion of their life. So these are the life stages of a low mass star. In the main sequence, hydrogen will fuse into helium in the core. The red giant hydrogen fuses into helium in a shell around the helium core. Helium core fusion, helium fuses into carbon in the core, while hydrogen fuses into helium in the shell. Double shell of helium, where both hydrogen and helium fuse in shells. And then you get a planetary nebula that leaves behind a white dwarf. This is not to scale. When high mass stars die in supernovas, you get extremely luminous violent explosions that can be seen from these curves, where their luminosity increases to something like 10s of billion times the brightness of the sun, more than 1,000,000 times brighter than a nova. A supernova is a one-time event. Once it happens, the star is gone. Nothing is left. There's two types of supernova. They're both about equally common. Type 1, which is a carbon detonation supernova, where a white dwarf builds up above that relativistic limit, the Chandrasekhar limit, collapses and violently undergoes simultaneous carbon fusion throughout. And type 2, which is the death of a high mass star. A carbon detonation supernova is when a white dwarf has accumulated enough mass, too much mass from its binary companion. The white dwarf's mass exceeds 1.4 solar masses. Electron degeneracy can no longer support it. It collapses, heats, and eventually the whole star simultaneously undergoes carbon fusion throughout. Because the whole thing is one ball of very hot pretty much, you know, it's very consistent structure. It's all just ball of hot carbon. And as it collapses, it all heats up. It all hits the point of fusion at the same time, and then the whole star goes off like a bomb. So type 1 supernova, you have a binary system. Leaving behind a white dwarf. It consumes material from its partner. As it grows, and then it detonates and explodes. A type 2 supernova is what happens with a large star. You get helium and carbon and hydrogen. Then eventually you get an iron core which implodes. The outer layers above the core rebound off the core because the core will pause due to degeneracy pressure and neutrinos being generated. And then you'll have a remnant core and a shock wave traveling outwards. Supernovae leave behind remnants, the expanded clouds of material from the explosion. So an example of this is the Crab Nebula, which is the remnant of a supernova explosion that occurred in the year 1050. You can see the remaining core of the star that formed the Crab Nebula in the center of it. It is a small, quickly rotating neutron star that pulses on and off because it's emitting beams of radiation. So the core will shrink and heat enough until it's hot enough for fusion. Nuclei will no longer, with larger charge, require higher temperatures for fusion. So the core thermostat is broken while the core is not hot enough for fusion, well, shell burning. And core fusion can't happen if degeneracy pressure keeps the core from shrinking. So this is a high mass star. It goes off with a path. So for a high mass star, hydrogen fuses into helium into the core. Then hydrogen fuses into helium in a shell around the helium core. Then helium fuses into carbon in the core, while hydrogen fuses into helium in a shell. And then you get many elements fusing in a series of shells. And then finally, you have a supernova that leaves behind a neutron star. Or if you have a very heavy mass star, that neutron star will actually be over its limit for support against degeneracy pressure and will collapse to form a black hole. So this process is basically cyclical. Stars form, evolve, and die, feeding material into new stars, which will form, evolve, and die. In their death, they send heavy elements out into the interstellar medium. These elements then become parts of new stars, and it repeats, steadily enriching the galaxy with heavier elements. So massive stars are better able to reach higher temperatures in their cores. They can fuse elements up to iron in their cores, and a very massive star will end its life as a supernova. So once hydrogen is gone in the core, the star will burn hydrogen in the surrounding shell, the core will contract and heat, and the outer atmosphere will expand and cool. Helium will get to fuse in the core as a helium flash in a smaller star. The star will expand into a red giant as the core will continue to collapse. The envelope blows off, leaving behind a white dwarf to gradually cool. And a nova will result from material accreting onto a white dwarf from a companion star. Massive stars become hot enough to fuse carbon, then heavier elements all the way up to iron. And at the end, the core collapses and rebounds as a type 2 supernova. A type 1 supernova is a carbon explosion occurring when too much mass falls onto a white dwarf. Type 2 is a heavy star explosion. All heavy elements are formed in stellar cores or in supernovae or in other violent events afterwards. Like supernovae are required, but for some elements, you actually need additional steps. And stellar evolution can be understood by observing star clusters. So it's not just supernovae that create the heavier elements. Sometimes you also need processes like neutron star mergers and stuff to kick you up even higher. So that was the end of chapter 22. That's the end of what's going to be on the test, which will be next week on Thursday. Let's see, we have about 10 minutes left. So I might start up chapter 23 and 24 about the core, some of the neutron stars and black holes. So some of the remnants of massive stars. So let's talk a little bit more about the deaths of high mass stars. We talked that fusion can continue until iron builds up in the core. It takes energy to fuse iron. So as the mass increases, electrons get pushed into the nucleus, forming neutrons. And degenerates the neutron pressure can now keep the core from collapsing. So the core will quickly collapse from something the size of Earth to something about the size of a city, 20 kilometers in size. The degeneracy pressure of the neutrons will support the core, and the core will become a neutron star. And that pause and the rebound of material as it strikes this neutron core creates a shock wave that moves out through the star. This disrupts the outer layers, expelling them out into space, and this is called a type 2 supernova explosion. This also releases this enormous quantity of neutrinos, which helps form this shock wave. So after a type 1 supernova, little or nothing remains of the original star. After a type 2 supernova, part of the core can survive. It's very dense as an atomic nucleus, and it's called a neutron star. And the final state of the object depends on the mass. So if the initial mass was about 0.1 to 0.8, it's a brown dwarf, 0.8 to 0.25, a white dwarf with mostly made of helium, 0.25 to 8, white dwarf with mostly made of carbon and oxygen, 8 to 10, white dwarf made of oxygen, neon, and magnesium, 10 to 40, you get a supernova explosion that leaves a neutron star, and greater than about 40, you get a supernova explosion that leaves behind the black hole. So very low mass, it's a planet, low mass, brown dwarf, intermediate mass, white dwarf, high mass, a neutron star, or a black hole. So some of the effects from supernovae, we get the creation of heavy elements, things like gold, silver, lead, uranium, all elements created in supernovae. They also enrich the interstellar medium by distributing those heavier elements to form the next generation of stars. And a nearby supernova could be devastating to life on Earth. Within 50 light years, it would wipe out all life. Within 100 light years, it could cause extinctions due to radiation levels, but there's no stars that could go supernova that close to Earth. And I think I'll stop there. So we'll continue this next week. So we will have the test next week, Thursday. Next week, Tuesday, we'll continue. Your homework and your slides and stuff are all due on Thursday next week, the 30th. Any questions? Well, see you next week. I'm gonna stop sharing. Make sure you sign in if you. Now I'm gonna end the meeting.